Part of the lecture. Come on. Well, that does not look as nice there as it does on my screen, but it's actually just small on my screen. It probably is that bad. Today, we are going to be talking about, oh, it's April Fool's. I should make some kind of big lie. I graded your test and the lowest score is a 98%. Yeah. I of course, haven't looked at them, and I started off with the big lie so nobody would, believe me and then say, he is the cruelest person ever. Yeah. Hopefully good April Fool's jokes. Okay, so we're going to talk about the particle nature of light. And this particle nature of light is in direct conflict with what we talked about last week. Last week we learned about polarization. Well, the last week or 2 weeks. Polarization. We learned about diffraction and interference. And those things can only occur if light is a wave. And now we're going to look at things that can only occur if light is a particle. And so, this is a real conflicting idea. And we'll talk more about this apparatus. I have other pictures. This is the only place I have this one that didn't turn out nice. So let's get into it. So first, just the definition of quantum. Quantization. Quanta means quantity, right? And if something is quantized, it comes in only specific values. So for instance, we could say that money is quantized in that you can only have 1 cent, 2 cents, 3 cents. You can't have 1.65321 cents. So money is a quantized, when I say money, of course, I mean currency here. Your bank, you can have the price for a share of stock that's, out to 5 decimal places, but, or a gas station can have the price of gas is, 198.9 cents a gallon. Yeah, but they're never going to charge you 0.3 cents, right? Because it's quantized. So quantized are things that have specific values. Now, we've talked about a few things that are quantized. For instance, electric charge. What values can you have for electric charge? Let's ignore quarks. I know that exists, and I did talk about it, but pretending there are no quarks, it's still quantized with quarks. It's just different numbers. What values can you have for free electric charge? Because quarks are not free. Plus or minus what? 1. 1 what?
Plus or minus n.
N. Yeah, you can have 1.602 times 10 to the minus 19 coulombs. You can have 2 times 1.602 times 10 to the minus 19 coulombs. 3 times 1.602 times 10 to the minus 19 coulombs. But it comes in integer multiples of 1.602 times 10 to the minus 19. You said n.
Integer multiples.
Of 1.602 times 10 to the minus 19. Coulombs. So that's a quantized value. Another quantized value is the number of people in your family. Right? People talk about 1.5 children. Ha 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 ha. For the average family. Well, yes, that's an average, but no family has 1.5 children. I have 4 siblings. Lovely, lovely people, by the way. But it's an integer number. Now, something that one of my friends at least claimed he used to use to get money off of college students, he would go to bars and find a bunch of people who looked like they were, history majors or something like that, strike up a conversation and then bet them something like a beverage that the average number of legs that people have is less than 2. And these history people say, no, the average number of legs is 2. And they say, have you ever seen a person with 1 leg? Yes. Well, then the average is less than 2 because you take 1 plus a whole bunch of 2's and it's, okay. Legs are also quantized for the most part, right? So that's what quantized means. Comes in only specific values. It doesn't have to be like charge where it's an integer multiple of one value. You can have something like we'll learn later, angular momentum that's square root of L times L plus 1. Well, square root of L times L plus 1 isn't an integer. But for any value of L, it's that times the units of angular momentum, h bar, for the angular momentum. But it's quantized, only certain values. So that's what we're going to be exploring in this chapter. But we're starting with the beginning of quantum physics. So we've already learned a little about quantization. I talked about electric charge. Another thing we learned about was resonance for a string. For a standing wave, you have resonance. And there are only certain frequencies that a string will resonate at. So you have a cello, and you bow that string, and it has its fundamental frequency, but then it'll have an overtone that's 2 times its fundamental frequency, another overtone that's 3 times fundamental frequency, and so on. But there are only certain frequencies that it can resonate at. So that's quantized. The frequencies of a wave on a string are quantized. A picture to illustrate it. Okay, going right past that because we've already seen standing wave pictures too many times. So, a clicker question just to make sure that people were listening to me. And you cannot answer until now. Chad, you're in. Anyone before Chad wasn't? One more. You can do it. There we go. Okay. Okay, now 14 people have the correct answer. There are 3 that weren't with me here. Let's start with the easiest one to show that was incorrect. A quantity can only have positive values. I talked about the charge of an electron. It's negative. So a negative charge is not positive, hence that couldn't have been the answer. Then we have the top one, that the quantity is very small. A lot of people think that this very small is what quantum physics is about. It's not. Quantum physics only gives you significantly different answers in very small systems. But it applies to everything. Just like relativity only gives you appreciably different answers if you have speeds that are like faster than a tenth the speed of light. But it gives you correct answers everywhere. But why would you use relativity if something's going 10 meters per second? It's a lot more complication than you need. Same thing with quantum mechanics. Why would you use quantum mechanics to try to describe the flight of a baseball? It's a whole lot more complication than you need. So it's not about things that are very small, but it tends to only be relevant for things that are very small. I have, 10 clicker questions, so make sure you don't lose those clickers. Blackbody radiation. Catastrophe! Well, that's my title. I tried to take a few slides out and get this all in one. Blackbody radiation. That is, an object is hot. It gives off energy in the form of heat. And we had 3 different mechanisms for heat. One of them was radiation. Radiation is electromagnetic waves. When something's hot, it gives off light. That's what an incandescent light bulb is all about. It's hot, and so it gives off light. I'm hot. Does that mean I'm giving off light? Yes, thank you. Why don't you see me glow?
It's not a beam thing.
Okay, it's not visible. What did you say, Jaron? Was it funny?
It's not dark enough.
It's not dark enough. If it was perfectly dark, you still wouldn't see it. Because I'm giving off light outside of the visible spectrum. Now, we shouldn't call it light at this point, right? Because light is visible light, technically. So I'm giving off electromagnetic radiation, but it's in the infrared region. Now, we've probably all seen on TV, actually, you guys are young enough, maybe you haven't seen this, but back when we were, bombing things in Iraq, every night on CNN, you would see pictures with the night vision with basically a black background and green foreground. Well, what the heck's going on there? They have a camera that's sensitive to infrared radiation, and since people with a body temperature of 37 Celsius or whatever are giving off infrared light, they can pick up that infrared radiation, and then they just give it a false color, the green, and you can see things in the dark because they are giving off electromagnetic radiation, just not in the region we can see. So people were studying this. And the best classical theory had a problem. The best classical theory, now notice these two graphs are reversed. It's hard to tell, but this is wavelength and this one's frequency. So here the wavelengths are going positive like that. That's going bigger, so that means frequencies are getting bigger like this. This one here is the opposite. Frequency is getting bigger like this, so wavelength is getting bigger like this. So the graphs are reversed in direction. And that's why the dashed lines are on opposite sides. But those dashed lines are the best classical theory as developed by Rayleigh and Lejeune. Or however you pronounce that. Once again, help me out. Toussaint is my French expert here. How would you pronounce that guy's name? Jeans. Yes, like blue jeans, like David Bowie sang about. That was close, right? Yeah. So they use classical physics to come out with an explanation for how the intensity of light should vary with frequency or wavelength. And what they found was actually a pretty good match if you were at long wavelengths or low frequencies. But when you got to high frequencies or short wavelengths, that is into the ultraviolet region, it was very off. And in fact, classical theory predicted infinite radiation at high frequency. Infinite radiation at high frequency means an infinite amount of energy per second, an infinite amount of power is being produced by anything that has a temperature greater than absolute zero. Doesn't seem right, right? I think Elmer Fudd would have said, there's something screwy going on here, because that can't be. And so they called it the ultraviolet catastrophe because it was a catastrophic failure of physics theory. And so people knew there is something wrong with our theory. It can't be correct because it predicts that everything is giving off infinite amounts of power. And so, of course, this becomes an area of study. And in October of 1900, Max Planck, a German physicist, got a telegram that said at low temperature, the variation in intensity with temperature has this mathematical form. And so Planck that night sat down, did a little work, wrote a postcard, sent it back to the person who sent the telegram, said, well, in that case, then we should have this, and it's pretty complicated, this function for wavelength as a function of temperature. And that equation he came up with in one night's work was correct. It perfectly fit the experimental shapes for the emission given off as a function of frequency when something is not at absolute zero. Now that's a huge success, right? Except for one little itty-bitty thing. What's the purpose of physics? To explain why things happen. What did he explain? He explained what happened, but not why. Explain what happened, but not why. I don't know what that is, but it's not physics. And so he had this equation that was correct, but didn't have a reason why, other than it fits. Right? It was just a fit to the data, basically. And so for a physicist, that's really unfulfilling. Hooray, I found the right equation. I don't know why. Now I know, on a test, I've had this happen. Hooray, I got the right answer. I don't know why. Little snippet of it. To get my PhD, I had to take 4 or 5 hour exams. One on electricity and magnetism, one on thermodynamics, one on quantum mechanics. I don't even remember what the other one was. Anyway, before the thermodynamics one, I got up every morning like at 5 in the morning and studied from 5 to 7. So I'd be ready for the test starting at 7:30. And I was looking over old test questions, and there was one that I had never understood. And I studied and studied it, trying to just figure out how it worked, and I couldn't figure out how it worked. Then I go up and open my test, and that was the first question on the test. But you know what I'd been doing for the last hour? I'd been looking at the solution to that, trying to figure out why it was correct. And so I could replicate the solution, but I had no idea why. So I know I got it right, and I figured that was God's blessing there, Okay, so Richard didn't quite have everything he needed, but, get him over the hump and get him into the PhD qualification. So, I felt really good about that. I felt that God blessed me, but as a physicist, that's not what you want. You want to understand why. So he got down to work on it. That's October, November, December. 2 months later, he comes up with a theory that explains why it would be correct, but it involved a really crazy idea. His crazy idea was that maybe light is quantized. That is, the energy of light can only be for a certain frequency this value, or 2 times this value, or 3 times this value. And so Plonk came up with his quantum quantum hypothesis? I get quantum condition and quantum hypothesis confused. He said the base energy you can have for any color of light is a constant, which is the self-named Planck constant, 6.626 times 10 to the minus 34 joules per time second, multiplied by the frequency. Which means that if you have a low frequency, that quanta of energy is smaller. For high frequency, it's bigger. But light will only come in integer multiples of that. Sorry. So you could have 1 times HF, or 2 times HF, or 3 times HF, but you can't have 1.67 times HF. And he said, if that is correct, if light only comes in these specific values, then using statistical physics, I can explain why my equation is correct. Now, he got a Nobel Prize for this. I think it was 1918. 1918, 1919, somewhere in that ballpark. He got a Nobel Prize for this idea that light is quantized, that the energy can only have certain amounts based on frequency. Now, he didn't actually believe this to necessarily be true, but he said, if it is, then I can come up with a physics reason for it. Of course, this was in 1900, and he didn't get his Nobel until 18 or so years later, so they had time to figure things out. Then we bring in the true believer. True believer is Albert Einstein. Now, I guess I got this slide in here. Notice this is anachronistic. 1886 and 1887. When did Planck come up with his idea of light being quantized? December of 1900. Okay, so this is 13 to 14 years beforehand. Heinrich Hertz had done some experiments to test Clerk Maxwell's idea that light was an electromagnetic wave. And so he was testing electromagnetic waves to see if they obeyed like light. And so he had a spark gap generator. Basically, you have 2 balls, and you put a voltage difference between them, and electricity goes jink. And that's how he was making his waves. And so he put alternating currents to make the arcs go. And he found that when these little balls were exposed to ultraviolet light, it worked better. And that is now what we understand to be observation of the photoelectric effect. But he didn't know that. He just made a little observation on the side of his lab notebook that, and actually it was about when I polish them, then it works better. But the polishing effect of the ultraviolet, we kind of gloss over that. I'd say it was the ultraviolet light. So before Plonk, there had been observation of a random idea, or a random, not idea, but outcome. And now we introduce Einstein. I hope we introduce him on this one. In 1905, what was Albert Einstein doing in 1905? He was working as a patent clerk. And from everything I've read, which of course is not very extensive, I'm not a historian, Einstein, after graduating from university, remember, have I talked about Einstein and math and that kind of thing? Okay, well, I talked about Newton. And Newton was, would you say, a good student or a bad student? He was a bad student. Why was he a bad student? Mostly because he was bored. Because the teachers weren't challenging him. He wanted to do these things that he found interesting, and they had boring things they wanted him to do. Different people are different, and there are plenty of people who are brilliant and yet simply bored with the curriculum that we as teachers give them. And so, we try to reach them in ways that we can. But the super brilliant, like Einstein and Newton, kind of defy that. And so one of the things that Einstein was just not interested in was math. So he's in the university and he has to take these math classes because he's a physics major and all. But he doesn't want to go to the class. So night before exam, instead of going to class, he just gets together with one of his buddies who turned out to be a leading mathematician in the day, and say, hey, what do I need to know for this exam? And so his buddy would tutor him the night before exam, and boom, he passed his classes without going to class because he wasn't interested. And so you hear his problems about math. No, if you can pass a high-level math class by just cramming the night before and never going to class, you're probably really good at math. Just don't like it so much. So, not the greatest student, but he loved some things, and he loved his job at the patent office. Because at the patent office, he got to look at everybody's nifty ideas and then say, now, will that work? And he got to analyze their ideas, and he loved that. And from, like I said, from what I've read, he and his buddies would get together in the evenings and go to the local tavern and have themselves a root beer or two and talk about papers that people had written in the scientific literature and make fun of mistakes they made and that kind of thing. That was what he was enjoying doing in life. This was before he married his cousin. His second wife was his cousin, by the way. First wife, the one that he had children with, was not his cousin. Well, in 1905, he wrote 3 very important papers. Have I not talked about these papers? Okay, one paper was on Brownian motion. That is, Brown's observation of a pollen grain in water, and it was jiggling around. And Brown said it must be cavorting beasties, i.e. microbial life, that was making it do that. And Einstein in his paper said, no. It's because we have that kinetic theory of matter, that molecules are constantly in motion. And if they're constantly in motion, those water molecules are hitting this really, really light grain of pollen. And Newton's law says the acceleration is equal to the change in momentum over change in time. Well, let's say the acceleration, I said that wrong. I said force at the end. Acceleration is net force divided by mass. So for something that has a really small mass, it doesn't take much more force to make it accelerate. And so he's actually seen the acceleration because of collisions between water molecules, individual water molecules, and the pollen grain. Second paper was on a special theory of relativity, which is why I think I must have already talked about this. And the third paper is the one he got the Nobel Prize for. And the third paper was his true believer paper. Now, Plonk in 1900 had proposed what if light has a quantized nature. That is, light is behaving like a particle. You can have one ball, you can have two balls, but you can have 1.6735 balls. And Einstein said, yes, that is true, that light fundamentally is a particle. It fundamentally is quantized and can only have certain energies, regardless of how it's produced. Actually, initially he kind of said, well, for a black body, you have the atoms with the electrons oscillating, and that's why it was quantized. And then later he said, no, it really is, no matter what the source of light, it's quantized. You only have certain packets. And so he called those packets the photons. So a photon is a name for the particle of light. Now, of course, if you think back about the history of light that we've learned, I do this a lot, don't I? Only when I say think back, though. If you think about what we've learned about light, we had, the tentacle theory, I think we can discount that one. But then we had Newton, a genius, who said light behaves as a particle. He had his corpuscular theory. But why did scientists drop the corpuscular theory?
Because of things like polarization, where it was only if it was a wave did that make sense.
Right. The first one was Young's double-slit experiment. The double-slit experiment said this can only happen if light is a wave. And now Einstein says, no, Newton was right. Light's a particle with a specific energy, and you can have one potato, two potato, three potato, four, but you can't have 1.6, potatoes. Photons. And of course, are people going to accept this idea?
Not off the bat.
Yeah, they're not going to accept it. They're like, you're crazy, okay? Newton was God. Yeah, in our opinions, he was pretty up there. And we discounted him because of Thomas Young's experiment. Why are we going to accept you, a patent clerk's new idea that says that, Thomas Young was wrong? But Einstein, who is, as far as I know, has never done an experiment, never did an experiment in his life, he proposed an experiment for other people to do to test his theory. And so that experiment is what we call the photoelectric effect experiment. It's what we're going to do in lab on Tuesday. And so for that photoelectric effect experiment, you shine light on a metal surface. Not hard to do. And it was already known that when you shine light on a metal surface, you could get electrons to come off. But we can compare the predictions of wave theory to particle theory. Wave theory says that the energy that you're going to absorb is just going to be proportional to the intensity. Right? You have the intensity, how much energy per second per unit area is striking the surface, and the energy absorbed is just going to be X% of that. And so wave theory says since the energy absorbed is proportional to the intensity, then that means that the energy of the electrons that come off should also be proportional to the intensity. So if you double the intensity of light, you should get electrons with twice as much energy coming out. Does that make sense? That makes perfect sense. Everybody in the day said, yeah, exactly, that's what's going to happen. Duh! And furthermore, Einstein says, now with this wave theory, what happens if you change the color? Yeah, you change the wavelength. So change color, that means change the frequency or the wavelength. What effect does that have on the intensity? Well, the intensity is a separate thing, so that makes no difference. Now Einstein says, now let's look at the particle theory. The particle says that I am hitting this surface with little particles of energy called the photon. And the chances of two photons hitting the same electron are virtually zero. I'm going to have a super high intensity before the chance of two photons hitting the same electron becomes anything significantly far from zero. So basically, the energy absorbed by an electron is just going to be equal to the energy of the photon, which is HF. And so that means the energy for the electron coming off should just be equal to HF. So it's proportional to frequency. So proportional to intensity or proportional to frequency. That's a very different prediction. And furthermore, since it's proportional to frequency, color makes a big difference. Intensity. How does intensity matter? No effect. So there's some clear distinctions for the predictions of the wave theory versus the particle theory. Now there is one more thing that I haven't talked about. When the light is absorbed by an electron, the electron is going to, first of all, unless it's right, the surface is probably going to bounce around. And what happens is it bounces around. It's going to lose some energy. So here we're talking about the maximum energy, not the energy of every electron. Because you can have energies with slower, or electrons with lower energy because of collisions. Furthermore, it takes a certain amount of energy to remove an electron from the surface. And so you actually have the energy should be proportional to the intensity minus what we call the work function, the energy that's required to remove an electron from the surface. So these are the equations you should have for the electron energy based on those two theories. So then we do the experiment, and we are going to do this experiment on Tuesday. And our apparatus looks just like this picture. Just like this picture. So what we have is a metal plate, and then there's a collecting wire. So the light hits that metal plate, and electrons come off the metal plate. Now, if the wire is negative, it's going to repel electrons. But if the electrons come off with enough energy, that is, change of potential energy is equal to Q delta V, right? So if they come off with enough energy, they could actually have enough energy to still go across that filament even if it's negative. And so what we do is we adjust the voltage here until we get to the point where no electrons will go from that piece of metal to the filament. So we measure the current and adjust the voltage. And when the current is 0, then we're balanced. So the kinetic energy maximum is equal to the voltage difference times Q, the potential energy difference going from the metal to the filament. And kinetic energy maximum needs to be HF minus the work function. And so we're going to be measuring this voltage difference. It called it VS there, so I guess I should call it VS just to match the symbols. And from that, we should have, if we plot, let's say plot VS, what is the charge of an electron? It's E. So if we plot the voltage versus the frequency, we should have a straight line relationship. And actually, the charge is minus E, so there's a minus there. But we should have a straight line relationship, and it depends on our signs, if it's going to be positive slope or negative slope. And the slope should give us Planck's constant. That's what particle theory says. Wave theory says if we plot voltage versus frequency, what do we get? Flat line. Very simple to tell the difference. So what does the actual graph look like? Well, you're going to look at it, and it's going to come after 3 experimental results here are discussed. Brighter light causes an increase in current, that is the electrons that are coming off of the filament, but not in the energy. So the voltage, the maximum voltage to stop them, stays the same. That's one result of the experiment. So maximum kinetic energy did not depend on intensity. Okay, here's what the graph looks like. This one here has the positive slope, depending, like I said, on what you're graphing. What they find is a straight line relationship. Well, right away, straight line relationship between the maximum kinetic energy and the frequency. Whose theory does this support? Einstein. So when people did the experiments, they saw, oh, the prediction of Einstein was correct. Thus, light must be behaving as a particle, not as a wave. The third one here is there is a threshold frequency, a minimum frequency so you have enough energy to overcome the work function. Right? Just like when we talked about taking a molecule from liquid state to vapor state. You have to have a certain amount of energy to break away from the surface. Same thing here, you have to have a certain amount of energy to break an electron away from the metal. If you didn't, the metals would lose their electrons randomly, right? And so there's a minimum frequency to have enough energy to break an electron free. Oh, there's a fourth one. This one here is there's no buildup. It doesn't take time before the effect kicks in. So you're not building up energy. Okay, let's ask a question about this. And it's open now. Who originated the idea of light being quantized? These are all real physicists. And I obviously got excited about some of their names, so I put them all in. Wilhelm Karl Werner Otto Fritz Franz Wien. Max Karl Ernst Ludwig Plonk. I'm sure Albert had a middle name, but I don't know it. All righty. One person said Hermann von Helmholtz. 14 said Max Karl Ernst Ludwig Planck. And 2 said Albert Einstein. The originator of the idea was, as most people said, Max Planck. He came up with the idea. Who is the true believer? Einstein was the true believer. He believed that light was a particle. Okay, why did Einstein and Planck both receive Nobel Prizes for the preceding work? That is, why was it so important? Not why 2 instead of 1. They were different years. I always thought they shared, but no, they didn't share. Different years. How do I know this? Because there's a Nobel website that tells you about all the physics Nobel Prizes or anything else you want to know. Okay. Now, I actually intended this question to be a discussion question. But we actually have a majority answer here. Their work showed that light is a particle. That's actually what I consider the correct answer, but it's not the scientific interpretation you would generally come up with. What do we say about the scientific method? What do your experiments have the potential to do? Disprove. So technically, it would be saying that light is not a wave. And so why do I consider the correct answer to be showing that light is a particle? I mean, that's not the way science works. You don't do experiments to prove yourself right. You do them because they have the potential to disprove you. How does that work out? Yeah. Because we have experiments that conclusively show light behaving as a particle and experiments that conclusively show light behaving as a wave. And so we say, like, well, goodness, It must be both somehow. And as I said before, to me this illustrates a lack of understanding on our parts. We're still ignorant about what light really is because we say it has a dual nature. And Einstein, to his very big credit, was not derogatory toward light being a wave. He just said light is also a particle. And so we have the complementarity, I believe it's called. There's two principles that start with C, and I get them confused. But this one is the one that says that light has two natures, the wave nature and the particle nature, and in any phenomenon, you will see one or the other. But it's not going to be both at the same time. Now, I hope I took this question out of the questions for preparation for lab. I used to have a question about where do you see the wave nature in this lab? Because the old equipment we used a diffraction grating. And so diffraction grating was only a wave nature event. And then we used the photoelectric effect, which is only a particle event. So if you see that question, let me know so I can remove it. But the correct answer is, we're not using the diffraction grating with this equipment, but the old equipment we did. So now our understanding of light has a dual nature. So let's go on to X-rays. X-rays is another thing. And I want to know what people think of X-rays. I went to the dentist yesterday. They did X-rays. What were they doing? All right. 10.2.1.4. Okay, so we have high energy photons has the majority answer. Few people said low energy photons. One person said low energy particles that aren't photons. And 4 people said high energy particles that aren't photons. Now, the correct answer, we're going to talk about X-rays, but this was just, you go and have them and want to know what people are doing. They are high energy photons. High energy photons, is that a wave or a particle?
Yes.
That's speaking of it as a particle, but because it has a dual nature, it could be either way. So here's how X-rays are made. This is showing an X-ray tube. You have, notice the battery here, positive side. So this side here is really positive. This side here is negative. This loop right here is a circuit that makes that filament hot. Because it's hot, electrons get enough energy to overcome the work function and break free. And as soon as they break free, the high voltage over here pulls them across. And so electrons go slamming into this target, which in my picture is tungsten, but it could be copper or something else. They go slamming into it, and X-rays are produced. We have light that comes out. Now, this is exactly the opposite of the photoelectric effect. The photoelectric effect had you hitting a surface with light and electrons come off. They're called photoelectrons because light liberated the electron. It's still an electron. There's nothing non-electron-y about a photoelectron. It's called a photoelectron because light liberated it. Here it's just the reverse. You hit it with electrons and light came out. There are 2 things going on to make X-rays. First, you have the Bremsstrahlung, which is the German word that means breaking radiation. It turns out that physics demands if you have an accelerating charge, it has to give off electromagnetic radiation. And so if electrons go into this target and come close to a nucleus and interact with the nucleus and change their direction of flight, by changing the direction they're accelerating, they're going to give off radiation and also slow down. And so it's called breaking radiation because they're slowing down. Here's what it looks like. Your textbook is wrong with its figure. Your textbook shows a figure that looks kind of like a whale and going like this. If you plot it versus wavelength, it looks like that but reversed. They just reversed the wavelength plot. That's wrong. I'm not sure how you make that mistake. This is showing as a function of frequency or kinetic energy of the electrons coming off. And you see basically a straight line, basically, notice it's not perfectly, there. And that straight line corresponds to simply the energy, the intensity you'd come off if you had all of the energy of the photon at these different wavelengths. These here are a different thing. Those are not the Bremsstrahlung. The Bremsstrahlung is the smooth part. These characteristic radiation is when you have an atom with electrons. If it's something like tungsten, it has some electrons that are in n equals 1. If a collision with another electron makes that electron fly up to like n equals 5, something else is going to fall in. Right? It's falling down to the lowest state possible. And when it does, it gives off light, and that's what these are. So you notice this here is marked K sub alpha. K means that it's going from n equals something to n equals 1. So the end state is n equals 1 is what the K means. Alpha means that delta n equals 1. Beta means that delta n equals 2, and so on. So K alpha means it's a change in 1 and it ends at 1. If it's a change in 1 and it ends at 1, what did it start at? 2. Yeah. Beta means it's a change in 2 and it ends at 1 because it's a K beta. So that means it went from 3 to 1. And so that's what those characteristic X-rays are for. So you have two different pieces, one from the light slowing down, or not the light, from the electrons slowing down, and one from electrons falling in. Okay, we're out of time. I'll see you on Monday. Question?
So I have a question. Does this X-rays produce or have a continuous spectrum of frequencies? Mm-hmm. Can you explain that real quick?
Yeah, you have a continuous spectrum of frequencies because for the Bremsstrahlung, you're just slowing it down, and you could slow it down all in one fell swoop, right? It just goes, and stops, and then you'd have all of the energy producing a photon with that energy. And so that's what gives you the maximum energy here. So if you have 100, an electron that has E equals HF equals 100 electron volts, or kilo electron volts, then if you stop it all at once, it's going to produce this. If you stop it more slowly, like it's going, then you produce the radiation filling out the back.